pleasure to have Nikos Zygouras speaking to us about variants of the RSK and polymers. So Nikos, take it away.
Okay, thanks, Ivan. Thanks for organizing this series for a long period of time. Also, my thanks to Alexei. And I guess my thanks also to Clay Math for initially putting this whole program together. Hopefully, sometime we'll be able to get together again. So I'm going to talk about variants of RSK and polymers. The style of the talk will be more combinatorial, but John did a great job feeding us with lots of nice probability in the previous talks, so this will bring a balance. Okay, so I will make a quick review of RSK, even though I believe many of you know a lot about RSK, but I'm going to talk about RSKs. I think most of the people are familiar with what is going to be on the first slide. What is RSK? So RSK is a mapping of permutations of to a pair of what is called the Young tableaus. Young tableaus are these shapes the way you see them, and then we fill them with the numbers 1, 2, up to n. This can be, the permutation can also be a generalized permutation, so you can have repetitions of 1s and 2s and n's, and that's going to be of importance later on when we generalize RSK to cover cases that have to do with polymers. So a quick example about RSK is the following. So suppose that I have a Young tableau filled with the numbers in this fashion. And now I'm going to insert through this Robinson-Seston-Knuth correspondence, or RSK, the number 2. And here I'm going to highlight the word row. So I'm going to do the algorithm, which is of row insertion. In the next slide is going to be a variant of the RSK where we do a column insertion, and that will be important towards where I want to end up. So how the row insertion works. So number 2 tries to get in the first row and finds the first number which is strictly larger than itself. This is 3, and what it does is it's going to replace 3. And now 3 is going to be inserted in the next row in the same fashion. So it's going to find the first number, which is strictly bigger than itself. In this case, it's 4. It's going to replace it. 4 is going to be inserted in the next row until it finds a number which is strictly greater than itself. But there is no number strictly greater than itself. So eventually it's going to end up at the end of the first row. And in this case, it's going to provide a new Young tableau. So this RSK provides some dynamics, if you want, on Young tableaus, and dynamics have played an important role, pioneered mainly in dynamics by O'Connell and Alexei, Ivan, Leonid, and many of the collaborators. Now, let me go to the next insertion, which is a column insertion. And let's say again that I want to insert number 2. Now, instead of trying to insert into rows, I'm trying to insert into columns. So 2 is going to try to get inserted in the first column. And the rule here is that it will find the first number which is bigger or equal to itself. So in this case, the first number which is bigger or equal to itself is 2, which is equal to 2. And then it's going to replace it. So you don't see for the moment any change because 2 replaces 2. Now, the 2 that was bumped on the left-hand side is going to be inserted in the second column in the same fashion. So it's going to find the first number which is greater or equal to itself. Again, it's 2. It's going to replace it. And the 2 that was bumped is going to be inserted in the next row. It's going to find itself. Then we continue. So we follow this way. And then 2 is going to be inserted in the 5th column. Nothing interesting so far. Now the 2 that was bumped from the 5th column is going to be inserted into the 6th column. And then it replaces the 3. So it takes the space of the 3. And now the 3 is going to be inserted into the last column, where it bumps onto 4. It kicks 4 away. And then finally, 4 is going to be inserted in the next column. The next column is empty, so it just sits onto there. Okay, so this is very quick revision of the combinatorial algorithms, just to give you an idea of how it works. And maybe will motivate some algebraic representation of these insertions. Now, the next step, the next generalization is to have a matrix formulation of these algorithms. Now, instead of just having one word and inserting it letter by letter with the row or column RSK, I think that I have a sequence of words, W superscript 1, W superscript 2, and so on, whose number of letters so form a matrix W. So Wij here, you can think of it as a number of J's in the ith word. So we have this matrix of letters coming from words, and I can do the row RSK, or if I want also to do the column RSK, to map it into a pair of Young tableaus. The one is called P, usually, and the other is called Q. Now, a convenient reformulation of the Young tableaus goes under the name of Gelfand-Charlin patterns, which is a representation of these tableaus in terms of triangular arrays. And the mapping between tableaus and arrays goes as follows. So if I pick an entry here of the Gelfand-Charlin pattern, this encodes the number of letters up to K, up to I, sorry, in the jth row. Now, the reason that we prefer this formulation is that the next step we want to do is to stitch the two patterns together in the form of a matrix. So I have a P and a Q here. The bottom rows of each of the Gelfand-Charlin pattern are identical. And actually, the first row represents the length of the first row of each shape. The second entry of the Gelfand-Charlin pattern represents the length of the second row on the P and the Q tableau, and so on. Right, so if I do this stitching together, then RSK can be viewed as a mapping, as a bijective mapping between set of matrices. And this is a formulation that we will be using. Okay, so now the variant of RSK that I would like to work with. So this goes under the name of Birch correspondence. Birch correspondence works in two ways. So it does column insertion instead of row insertion. And also, it takes all the words of the matrix and reverses them. So if I have a word W, the reverse words will bring the n's at the beginning, then the n minus ones, and so on. In terms of matrices, so this would correspond if I had a matrix W, then I flip it in this way. And once I have this matrix formulation of a sequence of words, then I start doing column insertion. And then I get to get a matrix which is stitched up together of two Gelfand-Cherney patterns, and this is the Birch correspondence. RSK has been quite popular, but the Birch correspondence has not in integrable probability, but Birch correspondence has been used a bit less. Now, the approach that we have is a bijective approach. So I'm going to have a sequence of maps representing the combinatorial algorithm that I described earlier. And the basic map in the description of either RSK or Birch correspondence is this mapping here. So if you have a 2x2 matrix A, B, C, and D, the mapping will replace the first entry by the minimum of B and C minus A, and it will replace the bottom right corner by the maximum of B and C, and then I'm going to add D. So this is going to be the basic element in the algebraic approach of both RSK and Birch correspondence, but I would like to explain a bit this maybe a bit mysterious mapping. So going back to let's try to do this by following, by simulating some insertion. So let's suppose that we have a Young tableau, and then I'm going to insert some J's and some J plus 1s. And let's say I'm going to insert WJJs and then WJ plus 1, J plus 1s. So how does this work? So if we look at the Gelfand-Cherney variables, so we have this Zij, which signifies the length in the ith row up to the letter J. So what will happen if I add a number of J's? So the row insertion will push some J plus 1s away, and then maybe the new length up to the letter J is going to be here. And then we have two options. The one option is that Zi plus J is less or equal to Zi plus J plus 1. This means that I haven't kicked away all the J plus 1s. Or maybe Zi J prime after the insertion of the WJJs is bigger or equal to Zij plus 1, which means that I have exhausted all the J's, J plus 1s. And now what I want to encode, and that's what happens in this entry here, is how many J plus 1s have been dropped to be inserted in the next row. So we can see that the number of J's that have been inserted will be, well, it will be the minimum of Zij prime after the insertion with Zij plus 1. And from this one, I take out this part, which is Zi and J. So if I look this relation, this is a relation that I'm having up here. On the other hand, now let's try to explain this relation, and this encodes the length of Zij plus 1 after I have inserted, let's say, Wj plus 1's J's. So this is going to be the maximum now of where the J's have stopped with how many J plus 1s I had before. And then to this one, to this new length, I'm going to add a number of J plus 1s. So this explains this second relation here. So I hope I gave you at least a motivation of why these 2x2 mappings are kind of fundamental. Okay. Now I want to go from this basic local move into 2 steps away. So first, I would like to see what we call a geometric lifting. So in the previous relation, I had an algebraic expression which was involving only max and plus. And here I want to change this to plus and multiplication. So this is called geometric lifting, and in this geometric lifting, so the geometric RSK, the basic local move of the geometric RSK is going to take this 2 by 2 matrix and map it in this fashion here. Right. The next thing I want to do is to go from this basic local move to the full set of local moves that encode RSK. And this will go as follows. So let's suppose, again, let's try to do a simple simulation here. So let's suppose that I had my original matrix W, and I have inserted the first 4 lines here, the ones marked by red. And I have obtained a new matrix. And now the next step, I would like to insert in this kind of inductive fashion, the green line. This will go as follows. So first, I'm going to insert this entry here. And this is going to happen by doing a local move on this boundary. So when I'm on the boundary, the local move, the 2 by 2 matrix mapping that I had above is going to be modified in some sort of trivial way. But this shouldn't bother us at the moment. Okay, then after I have inserted this first entry, I want to insert the second entry. And the composition of the local moves goes as follows. So I will do this 2 by 2 matrix transformation I described above. And once I have done this, I think that there will be some numbers dropping to the next line. And the number that have been dropped to the next line and then inserted to it are going to be encoded by another local move, this 2 by 2 matrix mapping. Let's do another last simulation. So now I'm going to insert the third entry. Again, I'm going to do a 2 by 2 local move here. There will be some numbers that will be dropped in the following row to be inserted in the following row. This insertion is going to be encoded by another 2 by 2 local move. There will be some other numbers dropping in the next line. And then I have the last local move. And this is the way that these local moves work. So the next one will be creating a kind of a cascade that will work in this way. So I'm not going to describe this in more detail. I just want to mention that this very useful description of piecewise linear mappings of RSK were first done in the classical RSK by Bernstein and Kirillov, and then with Neil and Timo, we lifted this to the geometric setting. Okay, now where do polymers come? Okay, so I'm going to state the result, which is as follows. So then let's look at the partition function of path starting at the upper left corner and going to the down right corner. And let's compute the Laplace transform. So using the RSK property, the RSK construction, and the number of properties that they are needed to be derived, then we can compute the Laplace transform as an integral, where in the right-hand side I have what is called here Whittaker functions. So the alphas that appear here is actually a vector, alpha 1, alpha n, and the beta is also a vector. And these are the parameters of the distribution, the log gamma distribution of the environment. So this is the inverse gamma. So we can think that the initial matrix that we have is a collection of independent random variables distributed in terms of inverse gamma distribution with parameters alpha I and beta j. And right, so having this expression, actually an expression of this form we derived in a previous work together also with Ivan. And this led about 7 years ago, Ivan and Alexei and Daniel Remenik to prove the Tracy-Widom fluctuations for the partition function, the point-to-point partition function. Okay, so what I want to highlight is some key points in the derivation of this formula. And a particular key point is that this volume preserving property here. So the meaning of this is as follows. So if I look at the geometric RSK as a mapping between a matrices and another set of matrices, when I look these matrices in the log variables, then this is volume preserving. So the way we proved this was by this decomposition of the local moves. So if you have a 2x2 local move, this is quite easy to show that it is the Jacobian is 1. And if you have many compositions of local moves, each one is volume preserving, so the final result is also going to be volume preserving. And one of the things, and actually that was a motivation to look at these volume preserving properties, was that we wanted to extend the geometric RSK to the case where you have a matrices environment which are symmetric along the diagonal. And the motivation for this was that earlier work of Baik and Reins, where they had looked last pass of percolation with also on matrices with symmetries. And right, so the volume preserving property extends quite nicely in this symmetric environment. And then this means that if you look at the log variables on the left-hand side, to the log variables on the right-hand side, then the Jacobian of this is 1. And once you have this, then you can also write the Laplace transform for polymers in this symmetric environment, which essentially will be, by reflection, polymers lying above a certain wall. Okay, so that was a story around 2013. And one thing that was bothering us that we also wanted to do at that time was a case of a perisymmetric environment. So this means that you have a matrix which is symmetric along the anti-diagonal. And then you want to basically describe the law of polymers in this way. Again, that was studied in a unified way by Baik and Reins. And one motivation for looking at perisymmetric environment is that in the last passes percolation, this will give rise to point-to-line distributions and LOE distributions and so on. In the polymer setting, you don't get, by looking at perisymmetric environment, you do not get a point-to-line last pass polymer, but you get a replica, and I'm going to come to this later on. Now, one thing that was missing in the extension of this approach was a volume preserving property. So there are certain combinatorial aspects that indicate that if you have a matrix which is symmetric along this diagonal, then the P and the Q tableau that you get when you do RSK or geometric RSK are sort of related. So here we want basically a volume preserving property between the set of independent variables, which is the upper left corner on the left side and the lower left corner on the right side. And actually this, we did some examples by hand. some mathematical computations. You do a mathematical computation, then you see that checking a 3x3 matrix, it is volume preserving, so it has to be volume preserving. But the tools we had up to here to prove this volume preserving property were not enough. And maybe let me try to explain very impressionistically why is this. So the way we had managed to establish a volume preserving property in this symmetric case was again through these local moves that I introduced earlier. And so if I look at the local move in this bottom left, bottom right corner, because of the symmetry, the star variables will be the same. When I do the local move, when I do the insertion of this variable here and this variable here, they appear in a neighboring sites. So a local move just captures both of them. And this was somehow quite important to have the volume preserving property in the symmetric case. However, in the per-symmetric case, when I insert at some point the variable that stands here through a local move, okay, I can check that this will not, the Jacobian will be 1, but that's not the end of the story of how the variable that appears here affects the whole construction. Because later on, this variable is going to appear in this way, and the effect that the variable is going to have in the second half is going to propagate to the whole set of independent variables that I have. So somehow the local moves that we had back then were not enough to capture this non-locality property. They were very local. They were too local to capture this non-locality property. Okay, so the resolution to this is through this geometric Birch correspondence. And let me describe the local moves. Okay, maybe you see the local moves in this way. Not very kind of inviting, but the thing I would like to highlight is the following, the way it works. So suppose now that I want to do a Birch insertion of this letter here. In the previous case, in the RSK case, the local move was happening in this quadruple. However, when I do a local move involving this green dot, this is going to change this part and a part far away. And then that's not the end of the story. Then in the second stage, it's going to change again this part and the next one. And so on in the following case. So if I want to insert this part here, the first step of the insertion is going to alter this and this. The next part of the insertion is going to alter again this part and then this one. The third part of this insertion is going to alter this and this and so on. So you already see that maybe you have a feeling that there is a kind of jumping that can be useful for dealing with the per-symmetric case. Okay, so we introduced this set of geometric local moves in the work with Elia Beasy and Neil O'Connell. And for this, we were inspired very much by some work of Dan Bettea that appeared, where he was having the encoding of Birch correspondence, but in the standard combinatorial setting. And he did this in an appendix where inspiration for this was, I mean, these local moves in the combinatorial setting were also derived in a different language by Krantehaller and Van Leeuwen a bit earlier. And I guess also inspiration for the work of Dan Bettea, at least that's what he mentions in his appendix, is the dynamics on Gelfand-Cheremin patterns studied by Alexei Borodin and Leonid Petrov. Okay, so we have this kind of combinatorial local move description of Birch correspondence. we can lift it here. And then the question is we have to derive some properties of this and see if they do the job. In particular, the property that we wanted is preservation of symmetries, correspondence in terms of mappings in terms of paths, and the volume preserving property. The volume preserving property, it's straightforward to check in this case. Okay, so let me outline the main properties that we derived and that were important in order to connect to the polymer. So the first one is the log volume preserving property. And as I said, this is straightforward. The next one was an extension to symmetric environments. Well, one thing that we have is if we have a geometric Birch correspondence of a matrix W, and then you would like to see what's the geometric Birch correspondence of the adjoint of this, then you take the adjoint of the original input. So in the symmetric case, if you do geometric Birch, then again, you have a symmetry in the same way that you have a symmetry with RSK. You have a set of independent variables in the lower part of the matrices. And then again, we can show that the volume preserving property holds also in this symmetric environment. The next step that we had to do is the following commutation diagram. And that's actually important when we want to relate the geometric Birch correspondence to polymers on a per-symmetric environment. So let's look what this commuting diagram says. So let's assume that you have a matrix W and you perform geometric RSK, and then you get the P and the Q tableau. Take this now matrix W and flip it vertically. Then you get the flipped matrix and then perform the geometric Birch correspondence. What you are going to get is a P and the Q tableau related to the P and the Q tableaus above, where Q tableau stays the same, but the P tableau has had another action, which is called Schutzen-Bezer evolution. And in geometric setting, then we use the geometric Schutzen-Bezer evolution. Again, there is a piecewise, there is a combinatorial description in terms of local moves of the Schutzen-Bezer evolution. Okay, maybe I would like to mention something that it seems there is more depth into it and has been quite fundamental in proving the commutation of this diagram. And this is the following local commutation. So what it says is as following. So if you have a P site and a Q site in some matrix, and then you want to insert, sorry, if you have, let's say this is a PQ site, and this is a P+1 site. And then you want to insert the letters, that the entries that stand at the PQ site and the P+1Q site. So it goes as follows. So you take the entry sitting at PQ, and then you do a geometric Birch correspondence. Then you take the entry that sits at P+1Q, and then you do an RSK correspondence. And then you go back to the entry that sits at PQ, and then you do a Schutzen-Bezer correspondence. That will be the same as if you exchange the values at the two neighboring sites. Then you do a Schutzen-Bezer at the site sitting just above PQ. Then you do an RSK at the site sitting at PQ, and then you did a geometric Birch at the site sitting at P+1Q. We don't have a a good explanation why this holds. We proved it, but I think maybe there's something deeper in there. It's possible that the new Young-Baxter technology can recover it somehow, but we don't know. Okay, so I'm going to connect now to polymers, and the connection to polymers is going to be based onto this commuting diagram. Maybe in a nutshell, what's the relation of a geometric RSK and Berge in terms of polymers? So geometric RSK will encode polymers going down and to the right, and geometric Berge correspondence will encode polymers or polymer partition functions going right and up. And maybe I can give a quick explanation for this through these commuting diagrams. So this is the commuting diagram I have of both. By the way, the correspondence between paths also extends when you have not just a single path, but k-tuples of non-intersecting paths. So here in this site, I have drawn a k-tuple of down right moving paths. And okay. And then below I have the k-tuple of upper right paths, moving paths. So I want to relate somehow to encode the partition of the right upwards moving paths. Okay, this goes as follows. So I'm starting from here and I do a column flip. Well, if you do a column flip, then the paths that were sitting here, now they will start in this corner and then they will move downwards to this set here. Okay, the next step, I'm going this direction and I do geometric RSK. And there is a standard fact that we used, it has been used many times, that the partition functions are encoded by the bottom row of the Gelfand-Cherney pattern, which is also called the shape. And now another fact, the last fact is that we are going now in this direction. And the point is that the shape of two tableaus, that the one has been recovered from the other through a Schuchenberger involution, they have the same shape. So the shape of the P tableau and its Schuchenberger that appears here are the same. In the combinatorial setting, this is a standard fact of the combinatorics of the Schuchenberger, which is through this J delta Can. In our setting, we can see it through these compositions of local moves. But I guess there's no point to go into this.
So Nikos, just to check, so the geometric Schuchenberger correspondence, this has a nice description in terms of local moves as well?
Right, yes. So it has very similar to the geometric RSK. And this actually already existed in Kirillov's paper when he introduced what he called tropical RSK, what we call now geometric RSK. He had also introduced the local moves of the geometric Schuchenberger evolution. But he hadn't talked about the geometric Berge correspondence in that paper. So yes, so geometric Schuchenberger has a very similar encoding in terms of local moves like geometric RSK. It goes again diagonally up in this fashion, but it doesn't touch the shape. Okay, so let's see what's next. Okay, maybe, right. So what do I want to say now? Okay, maybe just let me recap what we have done up to here. So, so the goal here was to have paths moving in a perisymmetric environment. And by doing this, flipping of the columns, then I'm able to relate paths going in a perisymmetric environment, moving in a symmetric environment. And I know how to do geometric Berge in this symmetric environment. And I have all the elements for the geometric belts to describe the law of these paths, going up and right paths. So viewed from the lens of geometric belts correspondence, in a symmetric environment, I can describe this partition function. And then I get the same formula that I was for the Laplace transform in terms of a single Whittaker function that I was recovering from the geometric RSK correspondence in a symmetric environment. Okay, but the two things, especially through what I hope I managed to convey, the two partition functions, so they have the same distribution. So being able to analyze polymers in a symmetric environment through the geometric Bells correspondence gives us access to polymers in a persymmetric environment. Okay, what are some consequences of this? Okay, the first one is I'm going to talk about replicas. So suppose that I'm looking at the partition function of a polymer in a persymmetric environment. I can decompose this according to the point where this direct path hits the diagonal. And well, the paths are independent, just the path moving upwards and below. So I can decompose the partition function going from the upper left corner to the down right corner as a product of two partition functions. And these are point-to-point partition functions because I start from here and I end up here. And then if I want to recover the partition function in the persymmetric environment, I just need to sum up over all the possible x's that the path hit the diagonal. So here I get the square of two partition functions, point to point. And if you expand the square of the partition function, this will actually correspond to a partition function of two independent polymers moving in the same environment and ending up at the same location. So, well, if this was also divided by the square of the point-to-line partition function, then on the right-hand side, I will have the probability of two independent polymers moving in the same environment, ending up at the same location. And right, so this is something that goes under the name of replicas. And replicas have been quite important in statistical physics, in particular, if you would like to study localization aspects. So maybe this approach can provide a path towards studying replicas for polymers, but this is only the first step, because what we have a description of the law of the numerator, but we need to insert also the law of the denominator. And so we need to understand the joint laws of the two things. Okay, the second consequence I would like to describe is, here's the sum missing, is a symmetry, which I already mentioned. So, well, let's look at the partition function in a symmetric environment, which actually by flipping over the diagonal can be encoded as a partition function of a path flipped above a wall. And in the previous work with Neil and Timo, we were able to compute this as basically the Laplace transform as an integral of some Whittaker functions. Now, in the new approach that we have, we can also compute the Laplace transform of this point-to-point persymmetric polymer in a persymmetric environment. And this is given again by the exact same formula. So the two polymers in the two different environments, they have the same law. Now there has been quite lots of interesting works in symmetries of polymers by Alexei, Michael Wheeler, Vadim Gorin, and then follow-up works by Galashin, which is more on the algebraic side, and by Daniel Dovern on the polymer side, and RSK flavor. But it seems to me that this kind of symmetry, it doesn't fit this framework. So if you ask me what's the reason for this symmetry, I would say that it's the commutation of those diagrams that I described, plus the fact that if you expand the Whittaker functions, there is something called energy, and this energy should have some invariance under this Schutzenberger and all these commutations that I described earlier. Okay, so I think I will stop here, and thank you for your attention.
Well, thank you very much, Nikos. We have time for questions for Nikos. So just feel free to unmute yourself and shout out a question. Does the Schutzenberger, or the Q Schutzenberger, does that play nice with the sort of Green's theorem, the polymer path interpretation of like, does it have such an interpretation in terms of paths?
Yeah. So what? So Schutzenberger is an action on a tableau. So the initial construction of Schutzenberger is that just you have one tableau, so you don't have two tableaus. You have one tableau, and then you start moving. And a basic fact about Schutzenberger, actually, I don't know quite the history and the motivation for this, but the basic, an important fact is that it preserves the shape of the tableau. And that was the fact that I also used to relate the path, the description of the output of geometric beds in terms of paths. Eventually, I went to a relation that the tableau and the Schutzenberger tableau, they have the same shape. So that's all that I can say. But it's not really a mapping. Schutzenberger is not really a mapping between matrices and tableaus or Gelfand-Charlin patterns. It's really an operation on the Gelfand-Charlin pattern.
Mm-hmm. Okay.
Nikos,
Right.
can you say something about the asymptotics for this formulas? Are this suitable for asymptotics, or
I think the more relevant person is Ivan. Ivan has done some works with Guillaume Barakant and Alexei. So you can almost write it as a Pfaffian, right? As a Fairholm Pfaffian.
Well, so in the half space McDonald processes, what we were able to do is certainly formulate, formulas, some of the spirit of what Nikos was writing, some kind of more in the spirit of almost like Fredholm determinants or Fredholm Pfaffians, but we were only able to actually do asymptotics for a very special case of the half-space McDonald processes, which are half-space Hall-Littlewood processes, for which there was an identity that actually write things directly in terms of a Fredholm Pfaffian. Otherwise, we had trouble controlling the asymptotics. It's possible that using techniques such as Yevgeny Dimitrov has recently used, maybe there's some hope in controlling the tails of these sorts of asymptotics and actually proving these things. But yeah, we could see the formulas coming out, but actually proving them was something that we weren't able to do. Yeah, we weren't able to identify kind of a completely general Fredholm Pfaffian structure. There were definitely Pfaffians sitting in the picture, or things kind of like Pfaffians, but not to the point of being able to do kind of the types of asymptotics we wanted in general.
Okay, thanks.
Yeah.
Mhm.
I have a question. It was shown like an identity, a relation between the insertion and the Schutzenberger involution. So I don't understand if you had explained. Yes, exactly. So
This is a local commutation.
this holds at the level of the geometric lifting
Yeah,
of this operation.
yeah, we proved it at the level of geometric. So that was actually Elia is responsible for this. So proving this commuting diagram, it was eventually boiling down to this relation. And okay, the proof is sort of by hands-on proof.
Does there exist
It makes you wonder whether there's something deeper or if this can be used for other things.
Does there exist a classical analog of this identity?
I don't know if it. I don't know. We don't know. But you could, right. So if you go from the plus multiplication to the max plus, then you can obtain a combinatorial version of this local commutation. But I don't know if something like this exists.
Thank you.
There is a paper of Kirillov which has many commutation relations. And actually, I think it has many more things that needs to be studied, and the meaning needs to be invented or reinvented. But this relation doesn't appear there. It's possible that you can trace it back if you do some Young-Baxter technology. Maybe you can derive it, and I think that would be interesting.
Okay. Any other questions for Nikos? Okay, so if not, let's thank Nikos again.
Okay, thank you as well. Am I the last one in this series?
Yes, I think you are. Right,
Okay.
so we've been doing this over the summer. We'll take a little bit of a pause. I think we will have some integrable probability talks this fall, at least that I'll be organizing. There are also ongoing junior integral probability seminars. I think there's two, in fact. One is called the Junior Integral Probability Seminar. The other one has a more clever name that I can't remember. And so I have people's email. I'll send word about things when we start doing it again. But anyway, thank you all for participating. I know many of you have been coming weekly, and thank you all for the speakers.
Okay, I guess, yeah. So I have been following most of the talks, and thanks for keeping us lively.
Anything to keep us from enjoying the summer. So just kidding. Anyway, so have a good one. I'll post the videos a little bit later, and I'll see you all soon. Bye.
Thank you.